Okay, so hi everyone, my name is Omer. I'm going to present my work about statistical curriculum learning. It's a joint work with Ron Meir and Nir Weinberger from the Technion. Okay, so the idea of curriculum learning is to order the data we show to a machine learning model in a way that improves its performances. This approach is simply inspired by the way humans learn from easier tasks to harder ones. Main frameworks of curriculum learning include order the data using predefined set of rules, order the data using the model's own performances, and train simultaneously both the model that orders the data and the model of interest. Many studies have showed empirically the advantages of these methods, but their theoretical understanding is still limited, especially from a statistical perspective. So to study the statistical benefits of curriculum learning, Shu and Tewari offer the following problem setting, in which we have one target task, denoted by M0, and T source tasks. And these tasks are just data distributions with a different underlying parameter. And we want to learn the unknown parameter of the target task using up to n samples. So to do this, we want to design an adaptive sampling policy that needs to decide how to allocate the samples among these tasks. Each task here is characterized by a discrepancy, which is the distance between a task parameter and the target parameter, and it is unknown to the learner. And the learning difficulty, which is the level of noise in the statistical model, and it is known to the learner. For simplicity, we assume that all source tasks share the same learning difficulty. And the motivation to use those source tasks is that it comes from the assumption that they are much more easy to learn than the target task. And if we also have and can identify source tasks with a low discrepancy, then their samples could be more beneficial for us. Okay, so first we try to understand what's the best we can achieve here in terms of error rate or risk. And for that, we consider oracle learners that have information that is unavailable to a practical learner, and we use their error as a benchmark. Okay, so the first one that was naively considered by Shu and Tewari, we call it the strong oracle learner, that knows the discrepancies of all tasks. This oracle learner can allocate all the n samples to the task that balances best between the discrepancy and learning difficulty, and achieves the best possible error rate. We call it the strong oracle risk. And our first hypothesis for the solution of this problem is to follow this strong oracle learner and to identify the best task or the optimal task. Okay, so in the spirit of curriculum learning, we start with the very simple setting of single source task, and we propose an algorithm that is based on elimination procedure. So we allocate half of the samples for each one of the tasks, and we estimate their parameter using the samples. So because we divide the samples budget just by a constant factor of 2, and because the source task is much more easy to learn than the target, if the estimated discrepancy is larger than the typical error of the target, then it must be that the actual discrepancy is too large, and then we can eliminate the source task. So we can use this condition to identify which one of the tasks is better, and we achieve the strong oracle risk. Okay, so we want to generalize this elimination procedure for t larger than 1, and still to achieve this strong oracle risk. But this is impossible. Why? Because estimating the discrepancy requires samples from the target task. Therefore, they have the same learning difficulty, which means that source tasks that are better than the target cannot be further discriminated, and that the strong oracle learner sets an unrealistic benchmark. So with this in mind, we introduce the weak oracle learner that knows what we call the weak oracle set, the source tasks that are no worse than the target task. These oracle learners seem to set a realistic benchmark and still achieves a better risk than the non-curriculum strategy that uses only the target task samples. And the conclusion here that the right approach to solve this problem is to eliminate useless tasks rather than finding the optimal one. Okay, so we still want to generalize this elimination procedure. but we are aiming for the weak oracle risk now. And the problem when we have T source task is that we must explore all of them, and we allocate n over T samples for each task. And now that we divide the samples budget by T, which is obviously not a constant, it results with a factor of T in the error estimation of the discrepancy. This is sort of an effective learning difficulty. And because of that, we might not be able to eliminate some of the source tasks that do not belong to the weak oracle set. And this is obviously a problem. And to tackle this problem, we suggest performing multiple elimination rounds. If we're able to eliminate some of the tasks in one round, then we can estimate the discrepancy with a better resolution in the next round. We want to decrease this effective learning difficulty going from one round to the next one, hoping that we have enough rounds to bring it below the learning difficulty of the target task, because then we can identify the weak oracle set. Okay, so we proved that this algorithm results with a superset of the weak oracle set. And the question is, when is equality achieved? When can we identify the weak oracle the weak oracle set without any additional tasks? So to answer this question, we introduce this elimination curve, beta of tau, that given a problem instance, mainly the set of discrepancies, describes how many tasks our algorithm retains, given that the effective learning difficulty is scaled by tau. So more intuitively, it traces the number of retained source tasks along these elimination rounds. And if this curve has a fixed point, and you can see the blue curve has even 2 fixed points, it means that there exists a round in which we cannot eliminate any task. In that case, we cannot identify the weak oracle set. On the other hand, if this curve is below the identity line, it means that our algorithm effectively eliminates tasks, and we can identify the weak oracle set and achieve the weak oracle risk. Okay, so to complement our results, we also provide impossibility results using lower bounds of the minimax risk. And I'll just give a quick reminder about the minimax risk. This risk is calculated using sort of a 2 players game. First, we should choose the set of possible problem instances, and then the first player chooses the optimal algorithm knowing this set of problem instances, and the second player chooses the worst case problem instance out of this set, knowing the algorithm of the first player. And the risk is just the expected value of the error when this algorithm faces this worst case problem instance. And this dynamic sets a challenge, because on one hand, we don't want this set to be too large. For example, we want to exclude the case where all source tasks are useless, because it's not interesting. And on the other hand, we don't want the set to be too small, because then this problem becomes too easy. And we have a few examples in the paper that show that the minimax risk is 0, which also trivializes the bound. So we provide minimax lower bound for 2 problem sets. The first one introduced by Shu and Tawari, and we strictly improve it. And the second one introduced by us, and it matches the weak oracle risk. Okay, so one interesting property of this problem is that it is non-monotonic in some sense. So we demonstrate it using this example. We run our algorithm on several problem instances, and in each plot here we increase the number of tasks with different discrepancy. And as you can see, when we increase the number of tasks with high discrepancy, it has a very mild effect on the error, whereas increasing the number of tasks with a different discrepancy has a very drastic effect on the error, which is quite counterintuitive. Okay, so in summary, we introduced the weak oracle set as a realistic benchmark and minimax optimal for the statistical curriculum learning. And we also develop an adaptive algorithm that achieves this benchmark. few interesting future directions could be other learning settings, for example, classification, and other similarity measures. And if you are interested in more details, you can have a look at our paper that will be presented at COLT next week. And thank you very much. Any questions?